All right, great. So bringing us back to rational maps, as we discussed last time, a rational map is a map which isn't actually defined on all of X. It's an actual map from U inside X, a dense open subset. And as I was just saying, if X and Y aren't reduced, there will be people who say, ooh, is that really the definition of rational map? And I don't want to get into that quagmire. Okay. One important notion with these I just didn't have time to get to last time is the idea of a birational map. So I is birational map if, so one way to think about this is it's a invertible rational map. So what does that mean? It means there's a rational map which is inverse to it. If there exists pi prime, a rational map from X to Y, such that pi composed with pi inverse and pi inverse composed with pi. This is only going to make sense if both of these are dominant, right? You have to be a little bit careful about even trying to compose rational maps if they aren't dominant, because the image of one, if it wasn't dominant, could miss the domain of definition of the other. But these compositions are equal to the identity. And of course, when I say two rational maps are equal, because they're not defined everywhere, I mean, there's a dense open subset on which they agree. So the kind of thing you should think about here. So one kind of birational map is if I have any dense open subset, well, I can think of the inclusion of this guy as a rational map because it's a morphism of schemes. But there's a rational map back the other way, which is just take the identity on U and don't worry about what the definition is on any other. So this is birational. But there are other more complicated birational maps. So one which hopefully you've seen at some point is I could take any ring, I could take XY, XY, this is one of our kind of standard pictures, and I can include that into the direct sum K of X plus K of Y, where this map kills X, this map kills Y. And when I think about what that does on the level of schemes, if I take specs, here I have a line, here I have a line. Now I'm taking the disjoint union, and I take the map that maps this guy onto the x-axis and this guy onto the y-axis, right? And away from the origin here and the origin in both of these lines, this map is an isomorphism. So it's a birational map, but it's not an isomorphism of schemes. So being birational is genuinely a fair bit weaker. And you can even have, I should emphasize, there are integral schemes, which are not isomorphic, and there are birational maps between. So let me think if I can come up with a, yeah, I don't think we sort of have quite enough knowledge to discuss a good example of one of those, but you can have sort of a situation where like here you have A2 and you have a map that's generically an isomorphism, but there's like one point that has a more complicated fiber. This is the kind of thing that can happen. Yeah, let me not try to describe this precisely, but there's a notion of what's called a blow up, where I have over A2 over every point other than this one, I just take the point, and then over this guy, I take all the lines through this point. So this fiber is actually the lines going through my point. And so when I approach along here, when I lift this up, oh, there's something I'm approaching on, and that's the point that I hit here. So yeah, I just wanted to make sure we covered this definition, a theorem, which is sort of easy, but the proof in Vakil involves a very kind of scary diagram because you just keep having to restrict to smaller and smaller open subsets. Is I yeah, I'm just worried that I'm missing a an assumption here. So let me just assume x and y are integral. Are birational if and only if inside X there's a subset U and inside Y there's a subset V, such that these guys are isomorphic. Right? If I have such an isomorphism, then obviously I have a birational map, right? Because just the isomorphism from U to V here gives me a birational map from X to Y. The isomorphism from V to U gives me a birational map back this way. So the slightly harder, but not that much harder direction is how do I, taking two birational maps, define these isomorphic open subsets. The proof is basically like, oh, you look at the domain of definition of one, and then you intersect with the preimage of the other, and once you've done enough intersections, you're okay. Yeah. Well, since x and y are integral, they just need to be non-empty. Yes, in general, if you have dense open subsets and you have an isomorphism between them, you get a birational map. And maybe it's really right that I don't need any hypotheses here, but I worry that something like this is necessary. Okay. All right. So, one reason to think about morphisms is just, well, the general kind of philosophy of modern mathematics is, oh, probably you should think about most objects in terms of categories and how they relate to each other. And you're going to be kind of constantly using those ideas. I think even kind of stronger than that, in algebraic geometry, one can say that everything is relative. So you almost never want to talk about properties of a single scheme. I mean, often you do, but for example, quite often theorems are stated not in terms of this scheme has this property, but this map of schemes. So we don't want to talk about properties of schemes. Well, we want properties of maps. And I mean, of course, any scheme has a canonical map to spec of Z. So usually when we define some relative property, we would apply that to a scheme if the map to spec of Z has that property. So one very common one is we can take properties of schemes we've already defined before. And say that a morphism, X to Y, has property P. So somehow morally one should say something like the fibers of the map have this property. But we haven't really talked about fibers, and you need to be more kind of careful about that. So I wouldn't kind of phrase it more mathematically in terms of fibers. If for all u inside y, and often will require all u affine, so all affine open subsets of y, pi inverse pi inverse of u to u has or just pi inverse of u has property P. So, for example, we can say that D is affine. So we can talk about an affine map of schemes. What does that mean? That means that for every affine open inside Y, the preimage of that guy is affine. Two. So for example, if I take a scheme X and then consider the subset where a global section of the structure sheaf doesn't vanish. So this is points P such that F is not in the maximal ideal of X and P for F O of X, X. This is always affine. And the map I'm talking about is the inclusion of this guy into here. So this inclusion is always affine. And why is that? Well, because if I take an affine open subset U, right, then XF intersect U, that's the preimage of U, is just this guy DF, which we know is spec of whatever functions on here are localized at F. All right, more generally, there will be situations where you have an inclusion which locally is of the form DF mapping into U, but there's no actual global F that achieves this. So for example, right, another situation where I have an affine inclusion is if I have proj of some graded ring S, and I'm looking at the inclusion of D plus of F for some F. In this case, so by affine communication, it's usually enough to check these properties on a single open cover, right? So if I check on proj for the open cover given by D plus of some GIs, well, now this is the inclusion of D plus CI into here, which we know this guy is spec of S, localize it GI, take the degree 0 part. And this guy in here is given by inverting, well, I want to say F here, but F doesn't necessarily live in here. This is the inclusion of D f raised to the degree of gi divided by gi raised to the degree of f. This is just the easy way to write down something of degree 0. So locally, this always looks like I'm pulling out the 0 set of a function. I'm looking at the points where a function is not vanishing, but it's a different function at each point. This f is, again, one of these weird things that's not a function. We're eventually going to realize it's a section of a line bundle. Okay. Cool. So, I mean, this is a sort of general kind of philosophy of if I wanted to apply some property, it's enough to apply it on here. And by affine communication, usually enough to check on one open affine cover. All right. And there's a word for this that Bachil uses. I'm using an open cover of the guy I'm mapping into. So this is affine local on the target. So this means that you can check the property by choosing an affine cover of the target and then checking the property holds for the pre-images of each guy in that cover. What happens sometimes, but not as often, is that you can check locally on the source, not the target. You'll also hear the target called the base, right? We're usually thinking about this map as some sort of structure map, something like this, where I'm mapping the spec of some local ring, and this thing is called the base, where I'm thinking of this as like some kind of bundle or family. So base sort of denotes that it's the indexing set of the fibers. All right, so other things that sort of follow this property are quasi-compact, quasi-separated, open embedding, or you'll hear this also maybe called immersion. So open embedding, right, that's a property of a map where I have X mapping to Y, and there's an open subset of Y that this map is an isomorphism onto. Embedding. There exists U and Y, such that this holds. All right, so this is, of course, a property that's enough to check on any open cover on the target. Yes. Does U have to be the image? Well, it's an isomorphism, so that implies that U is the image of X. Right? That requires that U is X is surjective onto U, and any element of U has an inverse image in X. So the important part is that it's an isomorphism onto its image, and that image is open. Right? There are also plenty of examples where, think about spec of A and spec of A mod I, well, right, this is, here I have this guy and I have a bijection, but it's a bijection onto a closed set, not an open set. Right. And so you could try to embed, define closed embeddings as something that looks locally like this. We haven't talked about closed subschemes yet because it's a little bit complicated, but that's kind of the rough idea of what a closed embedding is, right? Whereas an open embedding, well, it would be nice to say it locally looks like I'm inverting a function, but that's only some open embeddings. There are open embeddings where it's sort of more complicated than that, right? So for this affine guy, for example, right, the classic example of a map which isn't affine is any map of a non-affine scheme to an affine scheme. So A2 minus a point into A2, for example. Right, and then you could close this up in various ways, right? You could take, instead of A2, you could take P2 minus a point. Mapping to P2, right? And that, so neither of these schemes is affine, but this is a non-affine map. Whereas you can have affine maps between things which aren't affine. So for example, here, right, there's a natural projective closure of these guys, or add in a point in infinity here, add in a point in infinity here. And this is a perfectly good map. This is if I take proj of XYZ mod XY, and this is proj of K of XZ plus XY. Right, that gives you two copies of P1. Proj of this guy gives you this sort of projective closure of the two coordinate axes. This is still an affine map. If I take any affine subvariety here, the pre-image here is going to be affine, right? A subvariety of this guy just means remove finitely many points, but make sure you remove at least 1 point from each axis. And here, I'm going to take this P1, I'm going to remove a finite number of points from each of the P1s, and I'm going to get something affine. Are any questions? Oh, yes, I should have written YZ. I mean, of course, that's the same ring, but I was trying to write it in such a way that the map would be yes. Right, so the map from here to here is I map into one component by killing Y, I map into the other component by killing X. All right. Another example of something that fits this is projective. Right? So we call C from X to Y projective is for all open subsets U and Y affine. So this guy being affine, this is spec of A. So that means the pre-image of U is an A scheme. So C inverse of U is a projective A scheme. E, it's isomorphic too. proj s dot or s dot finitely generated. And I got slightly confused about this point, so let me just emphasize um, that this is taking A and adding positive degree elements to it. So maybe it's even better for me to write this. S is a quotient of A by adding in some variables, and the important thing is that the degree of xi is positive. I mean, if you want to. Um, I mean, it's worth noting here, I'm not requiring the map of A into here is injective. I'm just requiring that on degree 0, it's surjective. So somehow the picture you should have here is that I have y, and I take roughly y times pn for some n. Now let me put quotes here because we haven't defined y times pn, but this is the idea of what project, when I say like projective space, right? What's spec of, proj of A adjoin these x's if they're all in degree 1, that's like spec A times Pn. And then what I'm saying is X is a closed subscheme in here with the proviso that I didn't tell you what a closed subscheme is. But again, X locally looks like this, right? If I take the obvious open cover of Pn, the intersection of X with each one of those looks like I take a finitely generated A algebra and I mod out by an ideal in there. Mm-hmm. So xi has positive degree, but it doesn't have to be degree. Now, as Vakil points out, I can write this guy, I could choose a different S with the same proj where all these guys did have degree, but I don't want to require myself to do that. So it wouldn't change the definition if I had written one here, but you know, I like to keep my freedom. Okay, cool. So there are some more important examples of these properties that we haven't talked about yet. One we've mostly covered that's, again, very analogous to this one is finite type. Right? So we talked about what it means to be a finite type A scheme, but there's nothing special about having affine image for this. So we say that this guy phi is finite type if for all u and y, again, affine. So u is exactly as here, spec A. Pi inverse of u is a finite type A scheme. E, it has a finite cover such that every piece of the cover is spec of BI for BI, a finitely generated A algebra. So this is important because we're going to talk about finite in a moment. Finite type means I have a finitely generated A algebra. So the kind of paradigmatic finite type thing is B is a finite type, a finitely generated A algebra. I look at spec of B, mapping to spec of A. Finite type means you sort of locally look like that. So note, this is local on the source. Because it's just saying I have an open cover that has these structures. I might need to assume overall quasi-compactness. I could also say locally finite type and not require this cover to be finite. Um, um, yeah, so this is a different type of finite generation because I'm talking about an algebra, not a module. And I want to emphasize that because there's a potential real point of confusion about that coming up. The way you should think about this is the fibers are finite dimension. Right? So what this is saying, right, when I say BI is a finitely generated A algebra, I mean there's a surjective map from, now nothing's graded here, just the polynomial ring. Maybe I'll use a different letter to emphasize that. I have a surjective map to BI from this. So if I take spec of this guy, that's the nth affine space over A. So again, you might think of this as like AN times A, whatever the hell that means. But, you know, for example, I could take A to itself be a polynomial ring. And then you would want to think of this guy as a bigger affine space over K. So this is the kind of thing I want the freedom to do. Okay. So the important point here is, so BI is going to be identified with a closed subset in here. So I can think of spec of BI as a closed subset in here. So that's why I think of it as being kind of a finite dimensionality property. The only kind of notion of finite dimensional I have at the moment is being contained in here. Now, right, the thing you were bringing up, I think this is slightly different from what you were saying, but it's also relevant, is that if A is Noetherian, or if Y is a Noetherian scheme, or even locally Noetherian, right, then this is going to imply that X is also locally Noetherian. So if this is just kind of restating the Hilbert basis theorem. If Y is locally Noetherian, or let me just say Noetherian, and phi from X to Y is a finite type map, then X is Noetherian. And if the base Y wasn't Noetherian, well, then you would have to worry about, okay, this is an isomorphism after I mod out by some ideal. is that ideal finitely generated? So if my base is non-Noetherian, then you also have a slightly different notion of finitely presented, where BI is a quotient of a polynomial ring by finitely many equations. And if you're Noetherian, that's the same thing as finite type. So we don't, I'm not going to bother to talk about it a lot. But if your base wasn't Noetherian, you would have to worry about stuff like that. Put it there. All right, and on kind of open patches, this is just the Hilbert basis theorem. That if I have a Noetherian ring, and I take a polynomial ring over it, and I take a quotient of that, that's also Noetherian. All right, I know today is kind of a parade of different properties, but well, you were warned. That's what it says on the schedule. So a gazillion properties of maps of schemes. Probably the last one I'll get to is finite. So as I was saying, there's a real potential for confusion here. There are finite type maps, and then there are finite maps. So finite type, you should think of as being finite dimensional fibers. Finite, you should think of as being finite fibers. So from X to Y is finite. Yes. For all affine opens in U. So I'm just using the same notation here, that U is spec of A. Pi inverse of U is spec of B, where B is finitely generated as an A module. So this is a really important distinction, being finitely generated as an A module or being finitely generated as an A algebra. We talked a lot about this in my commutative algebra class. Hopefully you at some point talked about it. It is potentially confusing, but these are just the words we use. So the words for maps between schemes are finite type corresponds to being a finitely generated algebra. Finite corresponds to being a finitely generated module. Yes, right, right. Yes. A finite morphism is affine, yes. Oh, a finite morphism is affine. Interestingly, it's also projective. So if I look at S dot equals A plus B plus B plus B, so this is a graded ring where, this is in degree 0, this is in degree 1. So multiplication between things of degree 0 and degree 1 is A acting on here, right? And then all things in higher degrees, I just use the multiplication in B. So this is almost just take B and adjoin T, right? So I could think of this as B times T squared times T cubed, and think about this as a subring in here. So this is, again, this thing I was saying about uh, you can have different algebras that give you the same proj. So taking proj of B of t just gives me spec of B. But it turns out this also gives me spec of B. And what am I using here? Well, it's important that S dot is finitely generated as an A algebra. What are my finite generators as an A algebra? They're finite generators of B as a module. So if, might as well assume one of those is the identity, B1 up through BK are generators of B as an A module. They generate, or I should say, right, do it using this notation with a T. I think about B0 times T, which is just T, and then B1 times T, etc. BK times T are generators of this guy as an A algebra. Yeah. No. So again, it's almost this guy. It's all the elements of polynomials in B, except the degree 0 ones that don't lie in A. Right? So in all positive degrees, it's the same as the polynomials in B and T. But in degree 0, I replace the degree 0 bit of B with A in degree 0. But you could say, well, wait, can't you do this for any B and as any B algebra A? And the answer is yes, but this will only be a finitely generated A algebra if B is a finitely generated A module. Okay. So a finite morphism is affine and projective. And with a bit more work, you can actually show the converse is also true. If a map is affine and projective, then it's finite. So the way to think about this is a finite number of points is a perfectly good affine variety and a perfectly good projective variety. But if you have anything positive dimensional, in projective space, it's going to kind of close up around infinity, and it's not going to be affine anymore. So, oh no, I erased my example. This is terrible. So the maps that were here that I just erased are great examples of finite maps. So let's at least draw the pictures again. I had this picture, which was I had two copies of P1 that met at a point, which was proj of K of X, Y, Z mod XY. Right? And then I just had the two copies of P1 sitting separately, mapping onto these guys. So what do I see here? Okay, indeed, this is an affine map. That's good, right? And what's the sort of interesting thing I need to check? I need to check that there's an open cover of this guy where, by affines, where the pre-image is spec of an algebra that's finitely generated as a module of the functions here. So I have an open cover, which is remove this point and remove points on here. So the sort of interesting part of the open cover is I have K of XY, this guy, mapping into K of X plus K of Y. And indeed, this guy is finitely generated as a module over this guy. It's generated by 1, 0 and 0, 1. All right, so we only have a couple minutes left. What are the things we should know about finite maps? So one really important thing about finite maps is finite maps are closed. This is what's called the lying over theorem. What the lying over theorem says is if A is a subalgebra of B and B is finitely generated over A, then any prime in A is equal to A intersected with some prime of B. I'm having a lot of trouble. Okay. So in this case, where A injects into B, this is telling you the map is surjective. But in general, there might be some ideal that's the kernel of this map. And so the image would be the closed subset defined by that ideal. Yeah, yes. Which is the same as saying that the map spec of B, spec of A is finite. Okay, great. Another thing to know here is the fibers are always finite. And the basic reason for that is that, so choosing this pre-image, what does that mean? That means I'm choosing a closed subvariety in spec of B that maps down to my subvariety in spec of A. So the picture you should have in your mind here is, I don't have room to draw that picture, that, here's my Y, here's a closed subspace of it. What happens when I take the pre-image? I'm up here in X. This guy was irreducible. It corresponds to a prime. But when I take the pre-image, maybe it sort of breaks up into a bunch of components. But choosing this prime that's lying over this one is just choosing one of these components. And let me say Noetherian. Of course, I was about to say this pre-image has finitely many components, but that's only necessarily true for Noetherian scheme. And it's not literally true that finite maps are exactly the maps whose fibers are finite, but it's pretty close to true. That's sort of the mental image you should have. Sorry, it means that the image of a closed set is closed. Uh, Well, I mean, I just want to be careful, right? If I have A mod I and I have A mapping to that, A mod I is a finitely generated A module. So I do have finite maps that look like, here's this guy, I have something smaller and it maps in, right? So that's not surjective, but is a closed map. If I have a closed thing here, its image here will again be closed. Yeah, the A being injective here means that I'll have dense image. And so if I'm dense and closed, then I have to be the whole thing. So the kind of thing to contrast with, right, the kind of example of a non-finite map that sort of still has finite fibers is if I look at K of X mapping into K of X, X inverse, well, this is definitely not finitely generated as a module over this guy. And how does that manifest? Well, this is the inclusion of the affine line minus a point into the affine line. So its image isn't closed, even though it's dense. Right? So it's sort of failing to be surjective, but somehow you should think about that failure to be subjective as really a failure to be closed, a closed image. All right, we're out of time.